basic ideas behind it are, and why we still need to improve the way we think about risk, uncertainty, and decision making. The paper also shows that risk is not just a technical idea, it's a broad field that matters in many areas like industry, transportation, health, security, and investment. Okay, so to make it easy, I'm going to break down the core concepts of from this paper into five main parts. So let's get right into it. Okay, part 1, how do science and risk connect? When we say science here, we don't just mean raw data. It's about the process of producing the most reliable and justified statements based on what we currently know. The risk field has two big jobs. First, using risk assessment for specific, real-world problems like whether an investment is safe. And second, doing the general research to build theories, methods, and frameworks that everyone else has used. So, risk science isn't just about spitting out probability numbers. It's a way to understand what we know and what we don't know so we can make better decisions. In fact, as Aven and Hyde pointed out back in 2009, we should judge a risk analysis by the quality of its models, not just the final number it produces. But how do we actually go from science to a decision? Think of it as a pipeline. We start from data and information. That turns into evidence, which builds our knowledge base. From there, we evaluate the risk, and finally, we make a decision. But here's the catch. While evidence is built on data, the final decision always involves human values, goals, and policies. For example, think about a scientific committee. They sit right in the middle between science and policy. They assess the risk using scientific facts, but the final outcome is still influenced by the goals of the decision makers. Risk analysis doesn't make the decision for you. It's just one crucial piece of the puzzle. That brings us to part 2. What exactly is risk according to this paper? Honestly, there isn't one single definition that everyone on earth agrees on, but almost all good definitions share two key things. Number 1, there is a consequence to an activity or event. And number 2, there is uncertainty about when, how, or how big that the consequence will be. So, risk is not just a number. Risk is really a combination of consequences and uncertainty. That is also why risk cannot simply be reduced to expected value or a probability distribution. Those are useful tools, but they are not risk itself. Related to that, risk can also be described or measured in different ways. But the important thing is that risk metrics are not the same thing as risk. They are only tools for describing risk. For example, risk can be represented by a combination of probability and severity, or by a triplet of scenario, probability, and consequence. The point is that the metric helps us understand the risk, but it does not replace the full concept of risk. Then we come to uncertainty, which is one of the most important parts of the whole discussion. There are two main types of uncertainty. The first is aleatory uncertainty, which is the natural variation in a system. For example, we do not know exactly when it will rain tomorrow because randomness is part of the situation itself. For this type of uncertainty, probability with a frequency interpretation usually makes sense. The second is epistemic uncertainty, which comes from lack of knowledge. For example, if the data are weak or incomplete, then we may not know enough to assign one exact probability with confidence. In that case, using a single probability can create a false sense of precision. This is where other ways of expressing uncertainty become useful. One of them is interval probabilities. That means the probability is given as a range instead of one exact number. This is useful when we know the lower and upper bounds, but we are not confident enough to choose one precise value. Another approach is possibility theory. This is used when we can say how possible something is, but not how often it happens in strict statistical sense. A third one is evidence theory, which is useful when the evidence is too weak to justify one exact probability but still strong enough to support a structured uncertainty description. So, the main point here is not that probability should be removed. The point is that probability is not always enough on its own, especially when knowledge is limited. Another useful idea is strength of knowledge. This matters because two probabilities can look the same on paper, but the knowledge behind them can be very different. For example, a probability of 0.1 based on strong data is not the same as a probability of 0.1 based on weak guess. So, if we only write the number, we may miss an important part of the story. That is why probability should sometimes be reported together with the strength of knowledge supporting it. That way, the decision maker can see both the number and how trustworthy the number is. Let's move to risk management principles and strategies. There are three main strategies here. The first is risk informed, which means decisions are made using the results of risk analysis. The second is cautionary or precautionary, which means we should take protective action when the consequences could be serious and the uncertainty is large. The third is discursive, which means building trust through openness, participation, discussion, and accountability. So, good risk management usually combines all three, not just one of them. The risk management process itself is also pretty clear. First, you establish the context, then you identify hazards, threats, or opportunities. After that, you analyze causes and consequences, judge likelihood and impact, evaluate the risk, and finally treat the risk. So, risk management is not just one calculation. It is a complete process that goes from understanding the situation to making and implementing a decision. Another key idea is robustness. Robustness means a system can still work safely or effectively even when there is uncertainty, approximation, or disturbance. The goal is not necessarily to find a single best solution in one perfect scenario. The goal is to find a solution that works reasonably well across many possible situations. This is why robustness is so useful when the future is not fully predictable. Closely related to that is resilience. Resilience means the ability of a system to respond to threats, monitor what is happens, anticipate problems, and learn from experience. A resilient system is not just resistant to disturbance, it is also able to adapt and recover. This idea is especially important in complex systems where traditional linear thinking is not always enough. Then there is the idea of large and deep uncertainties. These are situations where the uncertainty is so big that traditional statistical methods are not enough. In cases like this, precautionary, robust, and resilient approaches become very important. Another useful idea is adaptive decision making. That means we do not assume one perfect decision exists from the start. Instead, we make a decision, observe the results, and then adjust based on what we learned. That is especially useful when the future is unclear. Another important part is risk criteria. These are often used to decide whether a risk is acceptable or not. But there is a warning here. If we rely too much on risk criteria, we may focus only on meeting a number instead of really understanding the risk. That is why decisions should be risk informed, not just risk based. Risk criteria are useful, but they should not replace judgment, context, or the strength of knowledge behind the analysis. Okay, finally, to the last part, the future of risk. We often use risk criteria to decide if a risk is acceptable or not. But if these criteria are too mechanical, people just focus on numbers and forget what the risk actually means. Criteria must be tied to the strength of knowledge. We should also follow the ALARP principle, which means keeping risk as low as reasonably practicable, focusing on finding the best practical solutions. And there is the idea of integrative perspectives. This is one of the strongest messages in this whole discussion. The future of the field should not be based on just one perspective. Instead, it should bring together traditional risk analysis, robustness, resilience, uncertainty thinking, knowledge assessment, and managerial judgment. That kind of integration is important if we want a stronger foundation for risk thinking. In the future, risk assessment and risk management should focus more on characterizing knowledge and lack of knowledge instead of trying to produce overly precise risk estimates in situations where the uncertainty is large. The field also needs better tools for dynamic risk assessment, emerging risk, complex system, security types application, and communication of risk to many stakeholders. Other important issues include intergenerational decision making, near miss analysis, and sustainability. So, the future of the field is not only about better mathematics, it is also about better judgment, better communication, and better understanding of what we know and what we don't know. To conclude, this topic shows that risk assessment and risk management are already well established fields, but their foundation still needs development in some areas. The main message is that we should not think about risk only in terms of numbers and probabilities. We also need to think about uncertainty, the strength of knowledge, robustness, resilience, and the practical judgment that decision makers must use. For me, the most important lesson is that good risk management is not just about calculating risk, it's about understanding uncertainty in a deeper and more honest way. That's all from me. Thank you for watching and listening.